Thank you, Alice. Thanks for the introduction and invitations. In this talk, I'm going to talk about Quasi-Monte Carlo method combined with important sampling. This is what John Watts with Zexin Pant in Zhejian University and Du Ouyang in Tsinghua University. Here's the contents. So let me show you some motivations. As we know, sampling is a central task in uncertainty quantifications UQ. For example, if we consider ellipses PDE with random coefficients here. So here's the random coefficient here, A here. So the coefficient is random. You want to choose, want to compute the solutions, we need to know the coefficient here. The coefficient here, if you, for example, if you model this coefficient by long normal random coefficient, in practice, this model can be approximated by finite dimension parameter vectors. For example, like this. In these models, the random vector is DIID standard normal here. So the dimension of this model is D. In practice, D is very large numbers. So we are handling a large number, a large dimension of random variables. So sampling proposal and random number generators are the cause of the sampling. We may ask three questions. The first question is, can we use more uniform points instead of Monte Carlo points? So the answers may be we can use the Quasi-Monte Carlo methods. QMC may have a faster rate of convergences than Monte Carlo. The second question is, can we change the sampling proposal here? For example, for these models, the proposal is the standard Gaussians. So can we change the proposal to another distribution to improve the sampling efficiencies? For this question, we may use important sampling to change the methods. The third question is, if we use Quasi-Monte Carlo methods and combined with important samplings, how to reclaim the efficiencies of it, especially for large dimension D. So I will try to answer these questions in this talk. First of all, let me review briefly the histories of Quasi-Monte Carlo. The term Quasi-Monte Carlo is due to these papers in 1952 who used connect sequences. As we know, Quasi-Monte Carlo points are designed in the Unicube in dimension D here. Actually, there are many constructions of QMC points in the literature, including digital nets and lattice rules. Another famous QMC points proposed by Chinese mathematicians is one-on-one methods in 1978. So let me focus on the numerical integrations by Quasi-Monte Carlo methods. So let me consider the integrals with respect to density phi here. So phi denotes by the density, and the capital phi denotes the CDF. So our target is to estimate an expectations of G x. X has the distribution phi here. So we can express this expectation by an integrals in dimension D with respect to the density phi here. So to use Quasi-Monte Carlo methods, we need to change the we need to generate a sample from the standard Unicube, standard uniform distributions. So we need a transport map here. So let me denote the transport map by the function t here. So t is the transport map from the Unicube to the proposal or the density phi here. For example, we can take the transport map by the inverse CDF. So this method is the inversion transformation methods. So we can result in a composite integrand on the Unicube F. So F is a composite integrand composed by G, composed by the T here. So for Monte Carlo methods, the conjecture points UI here is the random uniforms. It has a conversion rate of n to -1/2. For Quasi-Monte Carlo, the conjecture points UI are deterministic. We can get a better rate of convergences for QMC methods. In practice, we may use the randomized Quasi-Monte Carlo methods for error estimation, including random shift, digital shift, or scrambling methods. This slide shows the error rates for the Quasi-Monte Carlo. If we can use the Cosma-Halaka inequalities, the conjecture errors is bounded by two terms. The first term is the valuations of the integrands in the sense of Ardian close, and the second term is the stat discrepancies, which quantify the uniformness of the point set Pn here. So for Quasi-Monte Carlo methods with the stat discrepancy of these rates, if the function has a finite valuations, we can get an upper bound of almost n to -1 convergence rate, which is better than the Monte Carlo rates. However, the gains of Quasi-Monte Carlo depends on the regularities of the integrands F. For example, for unbounded integrands and non-smooth integrands, we can have an infinity valuation. So we may know expect an error rate of n to -1 here. In this work, we focus on the scrambled net integrations, which is a commonly used randomized QMC for unbounded function F. So the function, we assume the function is unbounded. Here's a pictures to compare the Monte Carlo points, Sobol points, and scramble points here. As we can see, Sobol points and scramble points has a better uniformness than the Monte Carlo points. Let me talk about important sampling. Suppose we have a proposal distribution Q here. By a change of methods, the expectation can be changed to an expectation with respect to the proposal Q here. But the function Gx is then transformed to Gx times Wx. Wx is actually a like ratio or regularities function here. To estimate the estimation, we may need the proposed transform map here. So we assume that a transform map T can generate samples from the proposal Q here. The T is the proposal transform map. So we can also have the composite function. So the result integrand is expressed by these formulas. The usual rate in Monte Carlo setting is to choose the proposal from a family of distribution to reduce the variance of the integrand in some sense. However, for QMC, the error rate depends on the choice of the proposal. A bad choice of the transform map or the proposal will make the integrands very severely for QMC. For example, if we result in a unbounded function which large boundary growth rates. So this is about the randomized QMC error rate for unbounded integrands. This is a boundary growth condition for the integrands. Suppose that there is a constant m such that the first order mixed derivative of the integrands is bounded by exponential function of m times the L2 norm square of the x here. Under this boundary growth condition, this paper shows that if the function has the boundary growth condition with the rate m smaller than 1/4, and the underlying density is standard Gaussian, and we use the normal the inverse CDF as the transform mat. This is the inversion transformation. Then the looming square error of the randomized QMC estimator is of order m to -1 plus 2 times the maximums of m and 0 plus an arbitrary small constant epsilon here. So the other rate depends on the rate, the growth rate m here. As we can see, larger growth rates leads to worse looming square error here. However, this result is no dimension independent rate. This rate depends on the dimension d here, which is is in distance m to epsilon, which is used for hiding the long term here. The long term have the dimension d here. So this is a dimension dependent rate for the RQMC. However, there is a QMC friendly case for this integrands. That is, if the m is an arbitrary small positive constant, so we can get a looming square error rate of almost 1/n here. For example, if the function has these forms, we can take an absolutely small positive constant in this here. So we can end up with 1/n, almost 1/n error rate here. So how about the error rate for important sampling under the Gaussian proposal? So suppose that the target density is the standard Gaussian. We choose the proposal Gaussian with the mean vector mu and covariant matrix sigma here. So for this case, the likelihood ratio can be computed by these two density like this. To change the normal distribution by the standard normal, we can use mu, the mean vector plus Lx, whereas which x is the standard Gaussian. L is the square root of the covariant matrix. So we can end up with an integrand with respect to standard Gaussians here. So here's the transforms integrands under the important sampling. So we can compare the boundary growth condition for the original function and important sampling function here. So as we can see, the small eigenvalue of the covariant matrix has an impact on the growth boundary rates for the important sampling function here. So we can see if we want to gain a better convergence rate, the small eigenvalue here should be larger than 1 here. This is our result in 20 and 23. The second part is our main result. In this work, we are going to propose a boundary dampening important sampling for RQMC. Our strategy is to design a wave function WT with the required smoothness from a parametric family, and then derive the transform mat or the proposal here. So we want to damper the growth boundary growth rates. So we will choose a special wave function WT here. For simplicity, we can see the product density. So our original density is IID distribution with the component has density 5 here. So we also choose the product proposal Q. So the proposal Q is a product form, a QJ. This major tuple here is J. So the transform mat is also has a product form here. TU is T1 U1 to TU UD here. So the weight function also has a product form here. So the weight function or like ratio has this form, Wj uj, a product of Wj uj. So if we have the formulation for the Wj, we can see that the relationships between the Wj and Tj. So if we have for given Wj, we can compute the transform map Tj by this formula. So if we have a Wj, the expressions for Wj, we can compute this transform map. If the Wj is easy to integrate, so we can have a closed form for Tj here. Actually, if Tj is a constant one, it reduces to the inversion methods. That's without important sampling. Instead, we choose the Wj from a one parameter family, W theta u. Theta is a parameter between 0 to 1/2 for dampening the growth rate of the resulting integrand. So here's the proposed weight function. Let eta be a function from 0, 1/2 to 0, 1/2, which is a differentiable monotonic functions, satisfying eta 0 equals 0, eta 1/2 equals 1/2. For theta is 0 to 1/2, we define the W theta u here is by this. The eta function we choose like this. We have a kind of a constant p here. The constant p is no less than 1, like this. So here's the definition of the proposed weight function. He has a parameter theta here. As we can see, if the theta goes to 0, the weight function will goes to the constant 1 here. So theta is if the theta is very small, so the weight function is very close to the function of 1. Here's the pictures of the weight function. Let me choose p equals 1, theta equals 0.2. So we can see the function have very symmetries over the 1/2. Symmetry over the 1/2. As we can see, when the u goes to 0 or goes to 1, the weight function decays very quickly, like this, very quickly. So we can help to dampen the boundary growth of the resulting integrand ft. So this is our main idea, to choose a weight function that decays very quickly when the u goes to 0 or 1. Before showing the main result, let me show you briefly the definition of ANOVA decomposition and mean dimension. Analysis of variance denoted by ANOVA decomposition. A function can be decomposed by 2 to d terms gu, which is a function depends on components in the set u here. U is a subset of 1 to d. So the ANOVA term can be defined by this formula, from these formulas. For the ANOVA decomposition, we have a variant decomposition here. So the variance of the integrand gx sigma square is a sum of the variance of the ANOVA terms here. So let me denote the variance of the ANOVA term by sigma u square. So sigma u square denotes is the variance of the ANOVA terms. So u and on defines the mean dimension by these formulas, which means this is the ratio of the ANOVA term contributes to the total variance. The ratio times the size of the index here. So this is called the mean dimension. The mean dimension. As we can see, if the mean dimension is a small number, the function can be approximated by as an easy function for Quasi-Monte Carlo, and the remainder is a half function, but it's tiny. So if the mean dimension is small, we can expect that Quasi-Monte Carlo has a better performance of even though the nominal dimensional is very large. For example, this is an example from this paper. This function is a smooth function in dimension D. For example, if the dimension is 500, we can calculate that the mean dimension is very, very small, very close to 1, the minimum of the mean dimension. So this means that even though it's a high dimension functions, actually is a very nearly adapted function for this function, which means this function can be approximated by a sum of one-dimensional functions. It is widely believed that randomized QMC gains significantly for high-dimensional problems with low mean dimension or effective dimensions. In this word, our seriality further shows that if the norms of the ANOVA terms GU decays as the product weight here, the randomized QMC combines with our proposed important sampling can yield a dimension-independent error rate, which is better than the Monte Carlo rate. This is our main result. Let me give you some assumption to establish our main result. The first assumption, we assume that the density phi x is a symmetric density. This condition is considered for simplicity. We can remove this condition by imposing some additional condition. But for simplicity, we assume that the density is symmetric. So we have the maximum value of the density, which is bounded. And then for any epsilon larger than 0, we assume that there is a constant C epsilon such that the right-hand side, the left tail of the density has a lower bound, is C epsilon times the CDF to power 1 plus epsilon here for any x is no smaller than 0 here. This is a key condition for our analysis. We can verify that if the standard normal distribution can satisfy assumption 8 here. And another assumption is talking about the norms for the functions. We assume the integrands in a function space here with the norm. The norm is the first order fixed mix L infinity norms defined by these formulas. We calculate the first order mix derivative partial VG the LQ in infinity norms Q to power Q, and the sum of all the first order mix derivatives here. So this norm is the L infinity norms or generalized L infinity norms defined by this. This is the GX the power of Q times the density over the if infinity. Infinity is defined by this, is the maximum of the density function here and here. So as we can see, if the function in this some function space, we can see that the ANOVA term also in this function space. If G in this function space. The ANOVA term also in this function space. So we can define the another norm, norm Q here which is the maximal of the norms of ANOVA terms, the norms of ANOVA term, which we be used in our numerical analysis. Actually, assumption B, if we use the standard normal distribution, actually assumption B is equivalent to the boundary growth condition here. For example, if this is the standard normal distribution, we can see the first order mixture derivative is bounded by this. You will put the formula of the standard normals, we can have this one. So you have a growth rate with the growth rate of 1 over 2q. So this assumption B is actually the boundary growth condition, but in another formulation.
Excuse me, can I ask a question?
Okay.
So there is how do you define finite infinity? It's a soup over X sum over some domain, but the domain is missing. Do you assume over the whole domain?
Yeah, the whole domain. Yeah, the whole domain.
Okay.
The whole domain. Infinite whole domain. Because this is times the density here. It's normalized density. Which one is no less than it's less than 1.
Yeah. So I meant the one on top, an assumption A, but it's fine.
Yeah.
Okay. So then how is assumption A verified for standard normal distribution?
This one, standard verification is our assumption. So for standard normal, it satisfies the symmetry density. But if we want to remove this condition, we may need another condition on the right tail of the distribution. So for simplicity, we assume that our density is symmetric.
So if the density is symmetric, you don't need a phi infinity to be bounded. Is that right?
Yes.
So symmetric density means that you don't need a bounded density then. But then how do you define GLQ infinity then in those cases?
GLQ. For this case, if the density is not symmetric.
No, yeah, if the density is symmetric but not bounded.
Not bounded. Oh,
yes.
Well, we require that the density is bounded. Yeah, we require that the density is bounded.
Okay, so then that's my question then.
If you
require it's bounded, if you require it's bounded, how is assumption A verified for the standard normal distribution?
Long normal. Sorry.
If you require it's bounded, that phi infinity is bounded, the density is bounded. How is assumption A verified for the normal distribution? Because normal distribution is...
Yes, it's bounded. So for the standard normal distribution, the density is bounded, and we can verify this condition for normal distribution. We can verify this one.
Okay.
I misunderstood. Okay, but we have the detail. Sorry. Okay.
I misunderstood.
Thank you. Yeah. How is this is the definition of our space function here. We have the norm here. Here's our key results on the error analysis. The conjecture point is a scrambled net with T qualities, the T quality parameter here. Under assumption A and B will require that Q is a number between 1 to 2. So we have some condition on Q here is 1 over 1 to 2. Then for any alpha between 0 to 1/2, we have the mean square error bounded by this formula. In which this is the norm we defined before. This is the norm defined before, like this. The maximal of the ANOVA terms, the maximal of the ANOVA terms norm. Then this one is system is constant, independent of the D and N, and this is the long N term. Gamma theta has a this expression, which depends on the theta j. We may want to optimize the theta j to minimize the upper bound in practice here. So the gamma v here actually is the norm of the ANOVA term divided by the maximum of the ANOVA term. You may think it is a normalized norm of ANOVA term. Normalized divided by the maximum of the ANOVA terms norm. So here is our main result. As we can see, this result gives a Loomis square error of m to 1 over 2 minus 1, almost minus 1 over 2 plus minus alpha. If we take alpha very close to 1/2, we can end up with an error rate of n to 1 over epsilon. So this result shows that use our important sampling methods, we can have a Loomis square error of almost m to minus 1. Moreover, when the density is the standard Gaussian, place randomized QMC without important sampling only has a mean error rate of m to minus 1 plus 1 over q plus epsilon. Okay, epsilon is any positive constant. So as we can see, if q is between 1 to 2, this rate is much worse than this rate, m to minus 1 or minus 1. So we can see that our important sampling can improve the weight of Planck's randomized QMC without important sampling for this case. If the ANOVA terms, the norms of ANOVA terms has the product form here. If the gamma v is bounded by a product form here, gamma j here, then we can see we can define the gamma j tilde if the sum of gamma j tilde is finite for some alpha. Then for any epsilon between 0 and 1, we can have a dimension independent convergence rate like this. The rate is n to the mean square error rate is n to minus 1 plus 2 alpha to epsilon minus epsilon. For example,
sorry, do you have time for a question from Shihab? He raised his hand here.
Sorry, excuse me.
I think Shihab has a question.
Okay.
So in your results here, do you assume that your proposal always comes with a product form? So you don't have dependence with respect to, you have some covariance or a correlation between the components?
No.
Or these results can extend to that case?
Yes, it can extend to that. If we want, if for dependent components, we can actually, if we consider a general Gaussian distribution, we can transform the general Gaussian distribution by standard Gaussian distribution. So we need one step to transform a general distribution by independent distribution. So we need a transform math, transform the IID to general.
Yeah, but if you have maybe more complicated distribution, like hyperbolic distribution, something like that, usually you cannot maybe like do it with like the multivariate Gaussian, where you can do Cholesky and then separate the dimensions. So that's why I was curious about that case.
Yes, that's a good question. So for this complicated case, we need some we need to find a transform math from a simple distribution to compressive distribution. The transform math, maybe we can use the machine learning methods to find out such a transform math, so that our theories can be applied for this case. So actually, in this paper, we didn't consider a general distribution like a dependent distribution.
Thank you.
Thank you. Okay. Okay. For this case, we can have a dimension independent convergence rates. For example, if the gamma j has a decation as a decays like this rate, j to minus rho is greater than 2 over q, and tj is has this rate log bj, which is in the case of Sobel sequence or the iterator sequence. Then we can set the theta j like this, theta 0 times j to minus log q with some constant theta 0 here. So for this setting, we can have a dimension independent Loomis square error rate actually close to n to minus 2 minus alpha star. Alpha star is defined by this. This is the result for this case. This case, alpha star is a positive constant here. So we can see that this rate is better than the Monte Carlo rate. The next is our numerical results. So we consider the special case of standard normal as the target density phi here. Our test function has this form here. Is a product of 1 plus j to minus rho gx. Gx has these expressions. For these product functions, we can compute the ANOVA terms here, fb, like this, ANOVA term here. For this example, we have gamma j. This gamma j is the upper bound of gamma u, the ANOVA norm of ANOVA term. We can compute the gamma j here is j to minus rho. As we can see, the function, the text function is in our function space with q between 1 to 1 over 2n. This one. For this case, the optimal choice for theta j is j to minus rho q. Is almost j to 1 over m for optimal case. So if we take rho to equals to 2 m's to 0.1 over 4. So the simple Monte Carlo doesn't work since the function is not in L2 for this case, because this is only 1 over 2, 1 over 2, 1 to 2, no bigger than 2. So it's no L2, it's not in L2. So the valence of Monte Carlo is unbounded. For this case, randomized QMC combines with our important sampling. We can have a dimension independent Loomis square error rates almost n to minus 0.7, because for this case, alpha star is 0.2. This is 0.5. So we can end up with a rate is n to 0.7. This is our prediction. So in our numerical...
Another question, I see.
Sorry, so for this example, it is not because you have a mean dimension that is equal to approximately 1 that you have something independent of dimension, not because of the importance sampling. Because if I see your function g, if I take the log, then it's an additive function somehow, right?
Yeah,
No?
yeah, we maybe have a very, very low effective dimension or mean dimension for this function. But
yeah,
but
so
for
my question is that when you say dimension independent, sometimes I'm confused. Is it because of the construction of the example and then you have a mean dimension that is already small, or it's a byproduct of your importance sampling? Because at least for this example, I mean, the mean dimension is already small, so maybe the importance sampling does not improve too much. Maybe I'm missing something.
No. Sorry, this has a very, you can see that this function is a very bad function for QMC. It has a very large boundary group rates for this function, although the function has very small impact for if J is very large. So, but however, this function is very large. For example, for Monte Carlo case, the function we made the variant unbounded. So this is not a good function for QMC, also not a good function for Monte Carlo. Maybe we may have a very low mean dimension or very low effect dimension, but he has a very fast, very large boundary group rates for this function because M is for example we take M is 0.25. It's very large number, very large amount of. So this function is a half function for QMC. So we can see the performance of the QMC if we don't use important sampling in the next slide. So in our numerical results, we compared four options. The first option is we use the inverse transformation for our transformat. So this is the planned randomized QMC without important sampling for option 1. Option 2 to option 4 is our proposed important sampling with different choice of TJ. The DJ is it depends on the theta j. We take the theta j have different case. The option 2 takes the theta j almost to j to minus 2 is underestimates of the optimal case. So the option 3 is j to minus 4. Is the optimal case for our choice of theta j. For theta j is j to minus 6 is our estimate of the rates of theta j. We can compare the performance of 4 options here. So here's the results of Loomis square error. This line, the blue line is the inversion method. That is the planned randomized QMC without important sampling. We can see the performance is is not as good as expected because it's very close to the rate 1/2. This dimension is 128 for this example. 128. It may be a high dimension probably. For the options. This green line is the optimal case of our proposed important sampling. It has a rate very close to the theoretical rate minus 0.7. This rise is 0.7, very close, very close to 1.7. The two lines, this line is the option 2. The next line is option 4. It's not as good as the optimal case. So we can see if we choose optimal case, we can have a better performance for this case. Okay, these are our results. The last part is the concluding remark. Actually, this paper has some limitations. Our results hold only for Q between 1 to 2, and that's no input for Q larger than 2. If Q is larger, that means if we have a slower boundary growth rate. Actually, if the Q is larger, it's an easier function for QMC. For larger Q is an easier function for QMC. We may expect have a better rate of convergence. Actually, this result didn't apply for this case. In our next paper, in our ongoing work, we intend the results for the fourth order mixture LQ norm. It's not L infinity norm. We intend the results for LQ norm. Q is a constant, any constant larger than 1, like this at this distance. This norm is LQ, not the L infinity. This norm can generalize the case of our L infinity norm here because LQ norm is bounded by L infinity norm here. So we can generalize, actually we can generalize the Q to the case, to the any Q, any case of Q larger than 1 here. So we can use another case of norm here. The next question is how to connect with the weight sublevel norm used in the following paper. In this paper, or many application of accuracy, we use weight sublevel form here. For example, if we use a randomly shaped lattice rule, it's usually use the weight sublevel form here. So how to connect with the weight sublevel form with our norm here? Here's the result. For more details, Nicolo and Coase use the weight sublevel norms for establish the error rates of randomly shaped lattice rule with unbounded integrands over the unbounded region RD. The norm is defined by this. It has weight, have a weight here, gamma U prime. So this is the rate, the weight. The size square is the weight function, which decays slower than the density function here. Yeah, this is the usual norms in QMC. We can generalize this norm to cover more severe functions here. We can replace this weight function by its density function, which is slower than the density function here. So this norm is generalized. This norm actually. Okay, as we can see that if the Q here we can use a general Q. If Q equals 2, our norms is bounded by the weight sublevel norm here. So actually we have we can cover more function in this norm here. Applies generalized Poincare inequality. We can see that our norm GQ defined by this can be bounded by this generalized the weight sublevel norm here. So actually for this case, it means that our result can apply for the functions in this paper, and some application of UQ in some papers. This is our ongoing work here. Okay. This is our paper. Thank you for your attention.